work on hydrology and geology for almost 40 years. He works for the Hennepin County Department of Environmental Services. He runs his own little consulting firm on the side. He's done EPA brownfield cleanup. 33 years ago, he co-founded and was the first president of the Minnesota Groundwater Association. So he's been around a long time. And Gil and I actually have something in common, because it says in here, he remembers attending college and grad school before the dawn of cell phones and laptop computers. So it's, with no more further ado, Gil Kabansky.
All right, thank you. When he talked about the Minnesota Groundwater Association, actually it was 34 years ago, and there was a group of us that got together and we started talking about forming this organization, and we decided we were going to do this, and we were going to try and figure out who was going to be officers. I got up, went to the bathroom, and came back, I was president. So nominate people when they're not around, because then they can't say no. It's the best way to do it. A little bit more history. I'm a hydrogeologist. I'm not a wetlands person. I'm a hydrogeologist. I've been involved with groundwater for almost 40 years now. And what I'm going to talk about today is to do with the fact that if you go back historically where we were and where we are now, surface water and groundwater were really considered two separate entities. And we learned a long time ago that they're not. They're all part of one great big dynamic system. And what I have found, I'm going to say alarming, is that I actually thought we were doing okay on maintaining the current status of our wetlands. However, my colleagues and some other people have basically told me that no, we're not doing that well. We're still losing them. And I think that's not good. And there's some reasons why, and I'll be talking about those. So again, I'm a hydrogeologist. I specialize in groundwater. I actually spend most of my time right now cleaning up contaminated properties. So at the county, I worked in a unit called the Contaminated Lands Unit. And then they decided to reorganize us, and they were looking for new names, and I suggested Earth, Wind, and Fire. The younger crowd didn't get it, so, but they ended up with the Land and Water Unit. So really, I spend most of my time dealing with soil contamination. Soil contamination has a direct consequence on groundwater. A lot of times your groundwater will be contaminated because obviously the avenue is through the soil into the groundwater. And when the groundwater is contaminated, it does move, it does migrate. We used to spend a lot of money pumping and treating contaminated groundwater. We realized after a while we were pumping out huge volumes of groundwater and removing a very small amount of contaminants. In fact, we were just transferring it from one media to another. We're taking it out of the groundwater and sticking it up in the atmosphere. And then when we found out, we turn off those systems and contaminant levels would come right back. So right now there's very little groundwater remediation going on that's active. There is some other consequences we've been looking at. There's soil vapor issues. If you follow anything going on in Minneapolis at a site that was called the General Mills site, there's quite a bit of soil vapor issues there. And I'm not going to get into that, but that's just another consequence of contaminated groundwater. Anecdotally, I was at a presentation that the commissioner of the MPCA, John Link Stein, gave 2 weeks ago, I don't remember. And he made a comment that nitrate concentrations in wetlands, they find is being more, they're there a lot more because of groundwater flow as opposed to surface flow. I was a little bit surprised to hear that. But that's, and in fact, I was trying to find a reference or some backup information for that for this presentation. I didn't come across it. So, but again, we're going to be talking about why wetlands are wet. And they're wet for a very simple reason. You have runoff, you have precipitation, and you have groundwater flow. And it's the groundwater flow that most people don't understand and they ignore. So let's just get going into this. And by the way, I was told that you're getting 1.5 hours of credit for this. So that means you have to be here for an hour and a half, right? Right?
Yeah.
And you're going to be here for an hour and a half?
Yeah.
Okay. I don't plan to talk that long. But if you want me to, I've got stories. I've been around. Really simply, why are we studying the relationship between surface and groundwater? Because in the past, we really did consider them two separate entities, and we didn't really study them like that. However, surface water and groundwater interact. And by the way, you have to understand, when I'm talking about wetlands, please understand I'm talking about wetlands, lakes, streams, rivers, any surface water body. And the reason is that most of the research for groundwater surface water interactions has been done on lakes. And we'll see a reason for that in a minute. But real simply, the surface water body, wetlands, are an expression of the groundwater. It's the water table. So we need to understand this dynamic of relationship because our increasing demands on water, water supply, water usage, how we're urbanizing areas is having a lot of consequences and direct impacts on the wetlands. So some fun facts. Surface water systems gain and lose contaminants, solutes, and water from groundwater systems. It's reversed, it's the same way around. Groundwater gets recharged and is also impacted by surface water. Some surface water bodies both lose and gain water from the groundwater systems. We'll be showing some illustrations of that. And groundwater serves as a large underground reservoir, and we'll see some numbers as to why it's really critical. Again, what we're finding is that we're impacting surface waters by our groundwater withdrawals, and I'll be showing some slides. Anybody here from the USGS? Excellent. I borrowed a whole bunch of their slides. They've done a wonderful study on White Bear Lake, and I'll be talking about that near the end of the presentation, but it's a direct consequence of pumping groundwater and impacting the surface water body. And what also is the simple fact that tiling, and I'm going to be hitting hard on tiling, is having a lot of consequences on wetlands. Because when you lower the water table, you're literally lowering that surface in those wetlands. Everybody know what the function of wetlands are? Anybody here not? Anybody that's in the wrong room, or you're here just for shopping at REI? And again, it's really simple. It's the hydrology, it's the habitat, and pollution control. And I don't like this because really we've made our wetlands into our nature's toilets. And if you look at that one, I do have a pointer here. If you look at this one here, what they have found is that when people seal coat their driveways, a lot of them use a coal tar-based sealant. Guess where most of that runs off into? It's in the stormwater ponds and wetlands, and it's loaded with polynuclear aromatic hydrocarbons, PAHs, many of which are carcinogenic. Benzoate is a carcinogen, and it's found in coal tar sealants. And Don Jakes, who was retired from the MPCA, told me several years ago that they estimated that the potential issues of dredging stormwater ponds, wetlands, and disposing of the sediment that's impacted with pH is maybe about a $7 billion statewide problem. And the problem is when you dredge out these sediments, they're impacted. You can't just dump them on the ground. You have to treat them as contaminated soils, which means a lot of them are going to end up going in landfills, which means we're going to fill up a lot more landfill space. But again, habitat is really critical. I think wetlands are one of the best areas of habitat. And you can't beat it by seeing the different, the variety, diversity of biota that's in those wetlands. Some simple definitions. Groundwater is that wet area that's under the ground that maybe you never see unless you've got a flowing well. However, when you're looking at wetlands, you're actually looking at the water table. It's groundwater. Surface water is that wet area you see on the surface. Wetland is the area delineated by it's hydrology, vegetation, and hydric soils. And then I always like this alternative wetland definition. It's an expiring lake or a lake wannabe. Mostly it's an expiring lake. And how many people do you know want to own wetland front property as opposed to lakefront property? So the water table is that surface under the land. We'll see some diagrams of this. But when it's at the surface, it's that water table expression at the wetland. Okay, amount of water that's on the earth. And you'll find many sources will have a little bit variations on this, but the main thing is that fresh water on the planet is 2.5%. If you get rid of the glaciers and the ice caps, you're left with mostly groundwater and surface water, and most of that is groundwater. And if you keep going through the scenario here, your swamps and marshes are 2.53% of only the surface water, which is 1.3%. Groundwater is a critical resource. However, we seem to focus more on the surface water because that's what we see. So some fun facts on groundwater. It occurs everywhere. You don't need a dowser to find your groundwater. Any place you drill, you will likely find groundwater. The question is, how deep? And will you be able to extract it? Because certain types of rocks and formations do not readily yield groundwater. If you go up to the North Shore, there's a lot of volcanic rocks up there. They drill very deep wells. They're about sometimes 300 feet down, and they're lucky if they can get a gallon per minute out of it. What they are is vertical reservoirs. And then there's some places out in western Minnesota where it has some very clay-rich overburden or unconsolidated deposits. Again, you can drill through that. You might find small sand lenses and layers, but you're not going to get that much water. Then there's places like in the southeast part of the state and around here where we have some excellent aquifers that are always used for providing groundwater. Velocity of groundwater, it's really slow. It just doesn't move. Foot per year, foot per decade. A fast movement is a foot per day. Example of a stream that is, we're talking about foot per second. So when things get in groundwater, they simply don't go anywhere quickly, which has some advantage to it, because if you have a contaminant, I mean, you have a known release, you don't have to rush out there and deal with that right away. You can manage it. And also, because of that slow movement, there's a lot of interaction in the soil or ground. And what we're finding is, and we've learned this over many years, is that there's a lot of bacteria that eat different types of contaminants. Petroleum, if you have a petroleum release, if you leave it alone, it'll go away. There's bacteria that's going to eat it. There are no underground lakes and rivers. You might find something in caves, but there are no underground lakes and rivers. If you leave here with one thought, there are no underground lakes or rivers. Different soils and rocks have different abilities to transmit the water. We'll be talking about that in a minute too. If you think about it, think about clay soil versus gravel. Water does move through clay very, very slowly. And then if you do any type of pumping or draining, such as tiling, you're going to locally lower the water table, and that's going to have some consequences. So just a simple diagram. Here's your land surface. Anything falling onto land recharges. A lot of it also runs off. It goes into the groundwater. The water table is that surface. Actually, it's defined by atmospheric pressure, and it typically intersects any surface water bodies. Aquifers are those underground areas that are used for potable water or for just any other type of groundwater development. Clay soils are not considered aquifers. I was told I had to have some math in here. If you were told there would be no math, they lied to you. So we have an equation. There will be a test on this. It's very simple. The Q over A, if you look at the dimensions, basically it's equal to a hydraulic conductivity times the gradient. And the gradient is defined by that surface right through here. So this is your higher potential and this is your lower potential. Obviously the water's moving from left to right. You have that distance L, and you can actually do a calculation to determine, you can back into the hydraulic conductivity, you can back into any of these numbers if you know certain parameters in your groundwater flow system. If you really want to know the velocity of the groundwater flow, you have to divide the area by the porosity, and we'll talk about porosity in a minute. Because you have to understand that when the water's moving through the ground, it's moving against the materials that are there. Think of sand. If you have water moving through sand, it's running up against the sand grains. So it's not just flowing, it's got this tortuous path around the sand grains. And the sand is retarding the flow. But if you take the cross-sectional area, most of it's solid. It's the porosity is what we're interested in. Sand gravel's porosity is around 30–35%. Clay's actually around 50%. See some numbers up here. Porosity, as you can see, soil, 55%, clay 50%, sand 25%. You can actually hide it higher. The issue is that are they connected? Are those pores connected? And that will determine if the water is going to move through the formation. Hydraulic conductivity, this is not a good example here. I apologize for that, but it has units of velocity. We typically talk about soils have materials having a hydraulic conductivity in centimeters per second. It's a common units we use. Clay soils, 10 to the minus 8 centimeters per second. Things like sand, 10 to the minus 4, things like that. And I threw this one slide in today just because I wanted to show something. When you're withdrawing water from the ground, as in the well, you have a cone of depression around that withdrawal point. And if you notice, if it intersects a surface water body, you're actually going to be pulling water from that surface water body. So now think about this. If you're putting in tiles, and let's say you're spacing them out away from a surface water body, you are literally lowering the water table. Over time, you're going to lower that water table and possibly start intersecting where that surface water body is, and you're probably going to start pulling water out of it. So you have the consequence of, I don't care how far you put the tiles out, you have the potential to be dewatering that wetland. Short history about wetlands. I hope most of you already know this. If you don't, great. They've been around since the Ice Ages. Really, I mean, they've been all. How many have ever been up in the big peatlands up north? Okay, I don't need to talk about it. Did you? I don't know. Did you ever fly over in helicopters, or were you just walking around? Here's the thing. I did a lot of work on peatlands. I worked for the Minnesota Geological Survey a long time ago, and we were doing an inventory up north, and we were flying around the peatlands in helicopters. It's a lot of fun. The thing that was really alarming is there's a lot of ditches, and there's old structures, and you wonder why. Well, they once advertised this area as rich organic soil for farming. It's really organic, but there's no minerals. It's not suitable for farming. And they actually were trying to drain those vast peatlands at one time. They also were trying to do it when they were back in the 70s, Power Old Peat. They were gonna harvest, by the way, not mine, peat, and dry it out and sell it as a fuel. If you think about it, you put more energy into the drying out than you're probably going to get out of it. So after the Civil War, I'm sorry, going back to colonial days, when they've looked at maps, they've noticed over time that we've been draining wetlands since that time. And after the Civil War, we really started draining when there was migration to the west and people started to farm more. The Prairie pothole areas of the upper Midwest and the Canadian provinces, and I have a slide on this, were devastated by these tiling and draining operations. And then as new farm machinery became around, it really became easier to drain these areas because you weren't just using farm labor, they started using actually steam-driven excavators and that. So they feel that by the 1920s, about 70% of the original wetland acreage had disappeared. And then actually, when you get into the 20th century, the U.S. government was very supportive of draining these areas. They provided engineering services. They actually shared costs for removal of removal of surface water. And then tile and open ditch drainage were considered conservation practices like that. Now think about it. If you were a farmer back then, you probably did this. I would have done it. Because that was what we thought was the way to make that land arable, was to get rid of those fetid swamps, those holes in the ground that seem to be just sitting there doing nothing but holding water. So if you get to the 70s and 80s, we figured that, I think this is a DNR number, 190,000 acres per year was disappearing, and the estimate is that we've lost over 50% of our wetlands. Back in the 70s, though, they started to talk about this more. They began to realize that there was not such a good idea to be draining all of this, and that's what led to the Clean Water Act and eventually the Wetland Conservation Act. But from talking to some colleagues, what I find out is we're still tiling and everything. This is Prairie pothole area. 276 square miles, 276,000 square miles, almost 20 million acres, and half of it's gone. And it's really most pronounced up in North Dakota and South Dakota. And there's actually been some really older groundwater research papers that were done on this, and it had to do with, this is where some of the first work was done on showing that groundwater flow into these wetlands was really critical. States with notable wetland losses, you can just see the slide up there. We've had these, that slide says less than 50%. I think that's actually inaccurate. I think it's at 50% or more. Old topo map. This is a Minneapolis 1901 topo map. And this is the city of Hopkins right here. By the way, this is called West Minneapolis. It doesn't exist anymore. But what you should notice is there's wetlands on this topo map. Everybody look at topo maps. Anybody here not look at topo maps? Either you're not going to say you look at them or you're going to lie to me. Whatever. Okay. All right, so you're familiar with them. There's wetlands all over in these old maps. I love looking at these old maps. In fact, that's how it's fun to find out. If you're buying a house, you might want to look at some old topo maps. And there's a person here from Historical Information Gatherers who actually, they have quite a collection of old topo maps, and they sell these as packages. And quite frankly, I love looking at them because you get to see what was there before development really occurred. So if you look at the more current map, here's Hopkins, and if you notice, the wetlands are pretty much gone. A good part of our development, urban development in the Twin Cities, if you look at the old topo maps, people have built on old wet areas. And when we do soil remediation, particularly in the Twin Cities area, we dig up a lot of what we call urban fill. It's ubiquitous, it's all over the place because they've filled in all over. And when you dig into this urban fill, it's loaded with debris and sometimes different types of contaminants, but we find it all over. And it's not uncommon for us to have a program or a project come in. We run a thing called the Environmental Response Fund. It's a large cleanup grant program. We'll have an application come in and they're digging up a site that has turned out by the investigative work to be literally an old dump. And when they start digging down, it's inevitable, they'll get down into organic soils. And you can tell, it was a wetland that had been filled in with anything that they could find available at the time. This is another topo map up Coon Lake Beach up in Anoka County. Notice the areas where they've kind of channeled and everything. This is a very current aerial photo of that, and that is that same area right there. But if you notice, look at the wetlands over here. Those are gone. Those are all gone. We've drained all of them. And I bet they have some pumps that pump 24/7. So if you look at the hydrologic cycle, this is the old versions you would always see. And if you notice, you have the precipitation, you have the surface runoff, evapotranspiration, evaporation, you have, they call it percolation, we call it recharge, and you notice it goes all the way out to the ocean. And the thing is, what's missing here? And it's really simple. It's that component where it goes into the surface water bodies. And actually, this isn't quite complete either because this should have aerials coming out because a lot of these surface water systems are flow-through systems. Groundwater will flow in on one part and it'll flow out on another part. This is what I really think is the true hydrologic cycle. We call it the hydro-illogical cycle, and this is something we go through quite often where, you know, we've got rain, it's fine, no one cares, and then we have a drought, and all of a sudden people get aware, they get concerned and everything, and then actually the panic here is all the legislators throwing their hands up, talking about all the things they need to do, and all of a sudden it starts to rain, and we kind of forget about it. So it's something we go through in cycles, and we just are probably in one right now. This is one of my favorite pictures. This is a sculpture by this guy, Isaac Porthole. Politicians discussing global warming. This is what it'll take. They'll get around to talking about it when it's really a problem. And maybe they'll come up with an answer. Okay, groundwater flow rates. If you notice the shallow stuff, the water table here, and by the way, notice that the water table is kind of a mirror reflection of the topography, the surface, the land surface. In your unconfined aquifer, we're talking about days, years types of flows. When you start getting into deeper confined aquifers, centuries, down here millennium, we're talking about thousands of years. When we pump out groundwater from some of the deeper aquifers, we're talking about water that's been there hundreds of thousands of years. It's been there a long time. And every time I think of people pumping water from some of our primary aquifers and watering their lawns and letting most of that water run off into the street, if I was the water czar, you would not be allowed to water your lawn. It's getting tougher done. It's a waste of one of our best resources. So, groundwater flow systems. A lot of lakes consider wetlands. You can have one that's totally outflow. All it's doing is contributing recharge into the groundwater system. Then you have those that are actually inflow, where you have water table coming down and you have all your flow lines going into the surface water. But this is the one that's really more common, the flow through, where you have flow lines coming in on one side and it's actually discharging on another. And we've learned how to try and evaluate those and how to measure that. The same thing applies for streams and rivers, where you can have a lot of flow into it, a lot of flow out of it. And then sometimes if the water table gets lowered for artificial reasons, you'll start just discharging from the stream directly into the ground. Out west, there's a lot of streams that disappear. Where they disappear is into the ground. They're discharging directly into the ground. Another equation. This one won't be on the test. The best way to measure groundwater and surface water components is to do a mass balance. But to do a mass balance, you have to know a lot of things. And it's really simple. To get the change in the water level of the surface water body, you need to measure the precipitation, how much runoff is coming in, evapotranspiration, surface water inflow and outflow, and then you need to get a handle on groundwater. Well, you can instrument most of these pretty easily, kind of, if you got the budget and money. This one might be a little bit harder to come up with, but you know, stream gauges, precipitation is not that hard. You can come up with estimates on this, but this was one of the hardest ones to come up with. How do you really measure how much groundwater is coming in and out of a wetland or a water body? So there's a lot of ways to do this. Water temperatures actually, just to get a quick handle on, is one of the best ones. Groundwater, water table is at the ambient air temperature, and in Minnesota that ranges from about 35 degrees up north to about 42 degrees in the southern part of the state. You ever walk in the shoreline of a lake and suddenly walk into a cold area? That's groundwater coming in. That's a groundwater flow coming in a surface body. It's not like being in a swimming pool, you walk into a warm spot. So just, if you walk along the shore, in fact, if you start kind of trying to get your feet into the sediment, you might find that all of a sudden you get into a really cold area. That's an indication you've got groundwater coming in. In fact, it's one of the easiest ways to figure out where you want to start doing measurements. So then you can put in piezometers and standard staff gauges. Seepage meters will be showing slides in that, and hydraulic potential manometers. That's a staff gauge right there. Piezometers. You know how deep you can put a piezometer in before you have to get a permit? 25 feet. So the health department that regulates monitoring wells, observation wells, water wells in the state gets a lot of indications that people are putting in piezometers 24.5 feet down. But if you go down deep, just be aware of it. If you're doing monitoring at any type of water body and you put in a piezometer or a monitoring well or an observation well, and it's 25 feet or deeper, you have to have a permit for that. So, piezometers. A lot of times we put them in nests, and this is a nested piezometer right here. And what it is, this is your standard water table observation well. In this case, it's a monitoring well because you're taking water samples, but it intersects the water table, and that's why you have a long screen interval. And then you can put in nested piezometers, and the reason you do this is you want to find out what the vertical gradient is. And what this is showing, and this is kind of an odd set here, but it's basically showing that you have a downward gradient because this water level, this water level, this water level are all going down. Now, whenever you put in a piezometer, you need to survey the elevation of that top of that pipe accurately. And usually we have these surveyed to 1/100th of a foot. Be aware though, when you put in a piezometer and you take a water level measurement down that pipe to that water level, you're measuring a water level in a pipe at a point in time. And a lot of times monitoring systems that are installed, they go out and they measure them 4 times a year. So you get measurements at 4 points in time. And one of the problems is if you have certain type of soil conditions, clay soils, silty sands, they have what's known as a time lag. So when you have a recharge event occurring, the response to the water level in that piezometer might take a while. It's a time lag. And sometimes if you're in really tight soils, the time lag can be months, half a year, 9 months. So if you're measuring a water level at a point in time, a couple of times a year, and you start to try and determine groundwater flow directions, I see these reports where it's going this way 1 month, Next quarter, it's going this way, and it has to do with the fact that there's these differences in how fast those wells are responding. So be aware that you're measuring a point in time. There's a lot of errors involved in measuring groundwater in piezometers. If you're in sandy soils, particularly sand, you're not going to have that as an issue. This is an illustration to show that you have a series of piezometers from this wetland to a ditch, and this is in the cross-section. You notice that the water levels are all going down. You can tell that there is a downward flow direction from this wetland to the ditch. And that again is an example of where, just think of this not only as a ditch but as a tile. You can be draining, no matter how far you're separated, you can be draining that wetland. Again, nested piezometers in line coming up to a wetland. You can, if you get the water level measurements in each well, you can start figuring out what your flow lines are, and you can see there's a lot of recharge here, but then when it gets closer to the surface water body, you're having a discharge into that surface water body. Hydraulic potentiometers. You don't see many of these put in. They're not cheap pieces of equipment, but basically what it is you install it so that you're getting a water level reading from in the sediments under the wetland, and you're getting a water level reading from the bed of the surface water body, and you get these differences. And in this case, if this is the groundwater and this is the surface water, you have upward flow into that surface water. And again, a lot of times you can have these set up so you get automatic recordings on it and everything, but this equipment's not cheap, so unless you are well funded, you're not going to be putting many of these in. CP's meters are a lot of fun. Back in, I want to say it was in the 70s, Dr. Hans-Olof von Kuchen, a student named Mark McBride, Mark cut off the top of a 55-gallon drum. And I'm going to give him credit for being the first one to come up with a CP's meter, and he might not be, but I think he is. But it was basically just, you shove these things into the sediment along the shore, and you have an opening that you put a bag, you clamp a bag onto it. And if there's groundwater flow up into the meter, it's going to start filling the bag. Now there's a lot of problems with how this is done. There's a whole document out there about all the error issues and everything. But believe it or not, these are used quite a bit, and they're really quite popular. You can just see the examples here, but this is a top of a 55-gallon drum that's in the near shore and everything. They actually have a device now for doing it in deep water too. I want to talk about just some lake studies that have been done now. I worked at DNR Division of Water back in 1980 to 84. And right when I got there, Big Marine Lake in Washington County had flooded. And I mean it flooded. It flooded out houses. The houses were built on the lake bed, but these houses were basically had water up to their eaves. And the question was, what was going on? It was a dry period. We were in a drought. And Big Marine Lake came up, eventually hit a spill well, and then cascaded into Big Carnelian, that cascaded into Little Carnelian. But there was this problem about where was the water coming from. Well, the USGS eventually did a study out there. This is the report. You probably can't see the date on it there. It is in the early 80s. But basically, they historically looked at the lake itself. And back in 1847, the lake was at 944 feet. In 1933, you can look at the difference in size of the lake. It went from 2,300 acres down to 933 acres. It dropped 11 feet in elevation, and back when they finally did the study in 1993, they were back up to 1,900 and almost up to that 1847 elevation. So there was nothing new here. This lake had been at those elevations at one time. It's just unfortunate some people built where they shouldn't have. This was one of the cross sections from the study they did with all the piezometers that they installed, but they really discovered that there was inflow into the lake from one side and outflow from another. It's theorized that during the drought period that this outflow wasn't necessarily occurring, and it was nothing but all inflow into the lake. And you can see in this one diagram down here, historically from 65 up to 85, the lake level actually came up, and it really kept just going up. But if you look at precipitation, surface runoff, it was mostly groundwater that was flooding the lake. USGS has been studying Williams Lake and Lake Shingobee Lake and River up in Hubbard County. They started Williams Lake in 1978, and they went to Shingobee, I think what was it, 1989. You want to see a place that has instruments. They have floating rafts out there that have continuous recorders for rapid transpiration, precipitation, lake levels, you name it. There's a lot of money has been pumped into this watershed. You could say they've been studying it to death. And the joke is, if you ask them, do they understand everything going on up there? And the answer is no. They still haven't figured it out. The guy who lives up there year-round has told me on a field trip a couple of years ago, every year he walks around the lake and he finds new springs. And the question is, have they been here before, or are they just kind of new, or what? But they've been trying to get a handle on the mass balance of this watershed. And like I said, they've spent a lot of money. And we've learned a lot. This study area has probably produced more master thesis and PhD dissertations than any other single body of water in the U.S. But they have been just studying the depth out of this. And there's been a lot of work also on just, not only just the hydrology, but on the water quality interaction and everything. But this is a study that has been instrumented, and we've learned a lot. But if you want to know what the answer is, do we really know everything going on? No, we don't. In fact, that's the thing I've learned over 40 years of dealing with groundwater. We still don't know what's going on. So I got job security, I think. In Long Lake, Michigan, they had a lake, Long Lake. You could see the lake bed, quite large. Water levels started dropping, and this is a guy walking across the lake bed. And they decided that they were going to put in a water well to replenish the lake. So they did. They put a well in right here, and they started pumping groundwater, quite a huge volume, and dumping it in the lake. The lake level never came up. And what they finally figured out was that all that water they were dumping in the lake was seeping right back into the ground, getting into the groundwater. They were just basically recycling lake water when it came down there. The well was quite expensive. And other people have tried this where they want to say, let's put in wells and augment our lake levels by pumping groundwater. And if you really come down, it's a waste of a resource. USGS study on White Bear Lake. This is a great study, and if you have time, you can download it. It's free. There's a lot of linear regression parts to it. There's a lot of math and everything, but it's a real comprehensive study. It's one of those studies that you don't normally get the budgets to do this type of work all the time, but they've pursued this, and there was political reason why this was going on. So what's going on is the lake shore has been retreating. That's a good aerial photograph of the lake. And if you haven't heard about this, you've probably been in a closet or something, because this has been all over the news for quite a while. Substantial decreases in, that's White Bear Lake. A couple smaller lakes had decreases. Most of them weren't really changing that much. Most of this was probably a lack of precipitation. But they had pretty good concerns about White Bear Lake. That's the general geology. It's pretty much underlain by glacial till. The key thing is the Prairie du Chien, Jordan. The Prairie du Chien is a carbonate aquifer. The Jordan is a sandstone. The Prairie du Chien Jordan is considered one aquifer. It's the primary groundwater aquifer for the Twin Cities area. If you have a municipality that has a well that's pumping, it's pumping from the Prairie du Chien Jordan. And when you put in municipal wells, we're not talking about 20 gallons per minute. We're talking about pumping 300, 500, 700 gallons per minute. So if you look at the lake elevation and precipitation, there's not really much difference there. I mean, you can look at the, annual precipitation drop here, lake drop there. It's been kind of up, lake's up. But look at here around 2010. The water elevation is coming down, but precipitation has been pretty much staying the same. So if you start looking at pumping of high capacity wells in the area, pretty much not much change here. Municipals here at total, but there's been an increase over time of municipal pumping. And this is all of the municipalities pumping, particularly from Prairie du Chien aquifer. And then if you start looking at just by aquifer alone, you see that most of that pumping has occurred in the Prairie du Chien. And the other aquifers, really not much to get any really change in pumping over all those years. So they started looking at elevations in groundwater levels in the Prairie du Chien. And interesting enough, they had a little bit of a rise over here. This is White Bear Lake right here, but notice the area here, the 10 to 12 foot decline area right here. We call that a cone of depression, and that's where municipal wells are located, and they're pumping a lot of Prairie du Chien Jordan water. And if you ever look at municipal pumping records, they'll be at certain levels during the year, but when summer comes along, they skyrocket because everybody's dumping the water on their lawns so they can have lush green lawns. So they actually did some isotope data, and this is not cheap. This is a lot of it. This is quite expensive. They do oxygen isotope data, and I'm not going to get into all the chemistry behind this, but what they found was that groundwater dating indicated that for the most part, the Prairie du Chien and other aquifers was pretty much groundwater, but they started finding lake water down gradient of the lake. Where's that coming from? Well, because of the oxygen ratios, it started to be coming from the lake. So when you look at the potentiometric surfaces around White Bear Lake, pretty much these are the flow directions. You notice the down gradient is from the lake, and this is where this is where most of the pumping's occurring, and this is also where they're starting to find lake water. So they did quite a bit of seepage meters around the lake. These are two different time periods where they did all these meters. Notice they're all near shore and everything, because what they're trying to find is that component of water, groundwater, coming in near shore. And if you look at the meters, these are, by the way, they measure this as a flux. They call it a flux, but the units are like a velocity. But just think of it as basically as a rate. The key thing is, if you look down here on the south and east sides, they had some really high numbers coming in. So what they were finding is there was actually quite a bit of groundwater flow coming into the lake, near surface, but the lake was dropping. Precipitation was almost the same. So what's happening? Why was the lake level dropping? So they actually did a bunch of temperature measurements, and here again, you'll notice that temperatures way down, by the way, these are centigrade. They had pretty much water coming in. To put it simply, they found that they had groundwater flow into the lake. But what they were able to conclude after quite a bit of money and time is that the bottom part of the lake was discharging. These are elevations. And if you look at the surface water elevation, this is your water table, and you look at elevations and piezometers in the aquifer, the water's moving from right to left. But notice the difference, 10-foot head difference. Water was going into the aquifers to the bottom of the lake, and it was pretty much a result of the pumping that was going on. So their conclusions were that the low lakes can be explained partially by precipitation, but mostly because of regional pumping. And that they were getting groundwater flow into the lake from the glacial sediments, but most of the water that was leaving was flowing out of the bottom of the lake into the underlying aquifers. So some people came up with some solutions. It's a White Bear Lake counteraction dish, whatever you want to call it. But, you know, they want to augment lake with additional water and then reduce the demand on the Prairie du Chien Jordan aquifer. Well, that's interesting. That's a primary drinking water source for most of the municipalities. How do you tell them to cut back on their pumping? How do you tell them to stop providing water? Well, I got a simple solution. Tell them to stop watering their lawns. It's a waste of water. That's one thing. But how do you augment the lake with additional water? Well, one of the solutions was go to the St. Paul Regional Water Authority. They get their water out of the Mississippi River. It goes into a chain of lakes. Here we go. We're taking surface water, moving it from point A to point B, and dumping it into the lake. Think of the energy involved in that too. You have to pump the water. Personally, I don't think it's a good idea. I'm not sure about this one, local industrial discharge water. Unless you're treating it, now you have to put in a treatment system for that water before you put it in the lake. Maximize the efficiency of pump use. You're going to probably gain a little bit there, maybe not. But they had some other, going to the Mount Simon Hinckley is one of the deeper aquifers. Again, you're going to spend a lot of money. It costs, it's a high energy use of pumping because you're pumping so deep. Why take good groundwater and dump it in a lake? I personally don't agree with any of these. I think just let nature run its course and stop watering your lawns. So, kind of at the conclusion here, wetlands are dependent on groundwater. That's why they're wet. They really are dependent on groundwater flowing in, and also groundwater is dependent on wetlands providing water to the subsurface. And we really need to keep this in mind, because what we do to our groundwater resource, how we extract that water, where we extract it, has this consequence of impacting surface water bodies. And we need to be doing a better job of characterizing groundwater discharge to wetlands. There's been a lot of good research done in the last 20 to 25 years. This costs money. USGS has been one of the primary agencies that have been studying it. They do good work. And that the Water Resource Office here in Minnesota is one of the leaders in this. And there's a guy named Don Rosenberry who's now in Denver. He's a student of Tom Winter, who's since passed away. But Tom Winter was one of the pioneers in this type of research. But they've turned out quite a bit of students who are pursuing this work. So what do we need to do? Most of us are some type of professionals. What I have found is that, quite frankly, we talk to each other. We talk to other people, except the people who really should be listening, and that's the public. We need to be talking to the public more about why these wetlands are important. I have a neighbor. It's not really a neighbor. They live a couple of blocks, but they got a wetland behind their house. And she's told me, she said, when are they going to drain that stinking fetid swamp? You know, and I said, well, you guys are doing a good job of filling it in because there's garbage in it. It's just loaded with trash. But it's like, why? Why do you think we need to get rid of it? It's serving a purpose. It's also helping you get rid of your trash, if you think about it. So you can talk to legislators. We really need to talk to them. And what we've learned, at least what I've learned over all the years, is during the legislative session, if you can get 30 seconds of their time, you're doing good. It's the off legislative session time is when you need to try and talk to them. A lot of times you end up talking to their aides. The aides will give you more of their attention, but we need to be talking to them, we need to be educating them. And if you think about it, what do legislators deal with? They deal with everything under the sun. Hydrology, wetlands, that's a really narrow area, but it's one way of getting the message across. You've got to take the time to talk to them. You've got to have organizations that talk to them. And education, it's more than just dealing with the lake issues. Like I said, a lot of the research has been done on groundwater-lake interaction. That's because that's where the focus is. People are concerned about lake levels, particularly when they either go up or go down. And guess what? They do that all the time. And they do it because of nature's response and how we are now impacting our groundwater resources. A lot of resources out there. If you just start looking, you'll find they're out there. There's no lack of them and everything. USGS, again, is one of the best sources. And this is one of my parting slideshows called Thinking About How to Manage Wetlands. Yeah, they're going to wait till it's drying up to maybe really start thinking about it. Maybe it'll be too late. Questions? Anybody want to ask questions? Otherwise, you can all leave. Yes, way in the back.
Regarding Winter Lake, I thought that one of the possible solutions was to get drinking water from that chain of lakes.
Yeah, and that's the St. Paul water supply system. And in fact, actually, the Metropolitan Council has been doing a good job on this. Instead of encouraging municipalities to put in new wells, the idea is let's have more of these municipalities being interconnected with other municipalities. And the reason is that it costs a lot of money to put in a new municipal well. St. Paul has a really interesting system. They have about a 28-day water supply system because they pump Mississippi River water into those lakes. They also have a backup system of water wells. Minneapolis gets all their water out of the Mississippi River. They got about a 48-hour reservoir. I mean, they're really dependent on the flow of the river. They don't have backup wells. But by providing water from the Vadnais Heights to the municipal water supply system is probably one of the better ideas. But let's not dump that in the lake. Let's not augment Lake White Bear Lake with water from that system.
Well, I just thought it was interesting too that we did a study once and all they would have had to do to connect the Minneapolis and St. Paul water supply would be to run a pipe a couple hundred feet, down Roselawn Avenue. And they won't do it because of politics. Well, that's dumb and dumber as usual,
When I first started in the Twin Cities, I was working at the Minnesota Geological Survey, and we were talking to a bunch of other professionals, and we approached the city of Minneapolis about how they really needed to augment their water supply system. They didn't want to talk to us, all right? Now, there's this movement about having municipalities interconnected. The Minneapolis water supply treatment system is underutilized quite a bit. They can provide a lot more water to other municipalities. They want to set the price. And the price they listed, the other cities are looking and says, no way we're going to pay that. So it just, the infrastructure is there, with the exception of a lot of the pipelines, but the infrastructure is there. It's just a matter of having some people sit down and talk to each other and come into an agreement. There's an idea. Yes, sir.
What's your take on the accelerated subsoil tiling that's been taking place for southern Minnesota, but especially even in the River Valley?
I'm not really aware of that. To be honest, I'm not aware of it. But talking to another colleague very recently, it just sounds like because of commodity prices, we're tiling like you wouldn't believe. And I hate to say it, but I always thought ethanol was one of the problems because everyone's trying to grow more corn. And what a horrible waste of crop. That's my opinion. I mean, you can do ethanol from other sources, but I understand there's a lot more tiling going on, and it's rampant, I guess. And I think it's a problem because we are lowering our water tables, and that is, again, going to impact any surface water body regardless of what the distances are.
Just as a follow-up to that, that's where we've got a huge educational gap going on because most of the folks that support tiling will say, no, actually we're storing more water. And I mean, there's just this huge middle block going on in agricultural areas regarding tiling. And I don't know